Hi children, welcome. Welcome to another class. Hope all are doing good, all are fine, right? In this class, we are going to discuss with, as you can see, chapter unit 13, Hydrocarbons, an important chapter from the first year topic organic chemistry, hydrocarbons, right? Let's straight away enter into the topic. So in hydrocarbons, basically we are dealing with four category of compounds. Number one, alkanes. Number two, alkenes. Number three, alkynes. And number four, benzene, aromatic compounds. These are the four category basically discussion that we proceed in the chapter, or we concentrate in the chapter. Let us go through one by one. First of all, alkanes. All of you know alkanes are called paraffins. Alkanes are called paraffins, para affinity. The least reactive system of hydrocarbons are alkanes. They are saturated compounds. They have sp3 hybridized carbon atoms with tetrahedral dangling bonds. Tetrahedral dangling bonds. They are saturated systems. Saturated systems. Para affinity. They are less attacked by alkali, acids, etc. They are least reactive in nature. Alkanes. Right? Having the general empirical composition, all of you know CnH2n plus 2, that is alkanes, right? A detailed talk on alkanes, their isomerism, examples, naming, etc. are coming in the first part of the chapter, that you need to take up and proceed with the each and every solved, unsolved examples from the NCERT, exercise part as well as textual content. What all things you need to go through? Naming, various examples and exercise questions, naming, IUPAC naming, which already we are learning in the previous chapter, naming of organic molecules. So that practice need to continue. Each and every organic chapter when we learn, you need to continue proceeding with the naming. Try to include common names also. Try to include common names also. For example, neopentane. Neopentane is a common name. Neopentane. You must know this is neopentane. This is neopentane. And what is the IUPAC name of neopentane? 1, 2, 3. So it is basically 2,2-dimethylpropane. 2,2-dimethylpropane. 2,2 dimethyl propane. Very simple system which I have commented. Neopentane common name and the structural entity and its IUPAC name. And there are some excellent questions you can find from the NCERT. For example, tetra tertiary butyl methane. They ask you to find out the IUPAC name of tetra tertiary butyl methane. What is IUPAC name of tetra tertiary butyl methane? What they mean? What they mean is this is methane. This is methane. What they try to tell you is replace this one hydrogen with the tertiary butyl group. This is tertiary butyl group. You replace this hydrogen with this group. Do that 4 times. You replace this hydrogen, this hydrogen, this hydrogen, this hydrogen with such groups. This group is called a tertiary butyl group. So what happens? Tetra 1, 2, 3, 4. Tetra tertiary butyl methane. They ask you to derive what is the systematic name. I am leaving to you practice. Of course, we are going to do such brilliant questions in the classes when we discuss the questions. Okay. So many NCERT questions. There's a great probability for the entrance exam to come. So please don't spare any exercise question from the NCERT. Our point of discussion mainly happens is preparation and properties of alkanes. Let us have a talk on preparation of alkanes. Preparation of alkanes. There are some important preparations commented in alkanes. Number one, catalytic hydrogenation. Catalytic hydrogenation of alkenes and alkynes. Catalytic hydrogenation of alkenes and alkynes. Say for example, ethene. Ethene treated with hydrogen in presence of platinum, palladium, nickel, etc. and heating if required. The hydrogen will be added over the double bond and you get CH3, where you can find ethene. Ethene is catalytically reduced to ethane. So ethene becomes ethane. Propene becomes propane. Butene becomes butane. Like that. So the given alkane converted to corresponding alkane on heating with the hydrogen and a catalyst. Platinum, palladium, nickel, etc. If it is palladium, room temperature is enough. If it is nickel, we need to heat it slightly. Many times we are using rainy nickel. What is rainy nickel? Rainy nickel means active form of nickel, powdered form of nickel. Powdered form of nickel. Why we use powdered form of nickel? When you make the catalyst in the powdered form, what is the advantage? The catalytic activity will be enhanced because surface activity is important for catalyst. So all these are heterogeneous catalytic action and is called catalytic hydrogenation reaction, and sometimes is also called Sabatier-Senderins reaction. Sabatier-Senderins reduction. Sabatier-Senderins reduction. Alkenes and alkynes are correspondingly converted to their respective alkanes. That is the reaction. What about if you take alkyne? Suppose I am taking ethyne. What do you get? Ethyne. CH triple bond CH. What do you get? Hydrogen with nickel upon heating. You see, one hydrogen will be added and you get CH2 double bond CH2 and the reaction proceed further. The reaction proceed further, you get CH3. So, we are starting from ethyne. You get ethene and from there to ethane. So whether you take ethene or ethyne, the final result is ethane. This is catalytic reduction. So for each unsaturation, you need one H2. For each unsaturation, you need one H2. There is one unsaturation, one H2. There are two unsaturation, you need two H2. So for alkene, you need one H2. For alkyne, you need two H2. For one multiple bond, one H2. So what will be the scenario if you take such a molecule? What will be the scenario? Suppose we are taking such a molecule. 1, 2, 3, 4, 5, 6. It is hexatriene. How many H2 will be required? Hexatriene. How many H2 will be required? 3 H2. 1 H2 to be added here. 1 H2 to be added here. And 1 H2 to be added here. And what is going to be your result? You are going to get 1, 2, 3, 4, 5, 6. You will get hexane. Hexatriene will be converted to hexane. Ethene, ethane. Propene, propane. Butene, butane. Pentene, pentane. Pentadiene, pentane. butane, butane, propane, propane. So any alkene or alkyne will be converted to alkane, number one. Number two, that is reduction of alkyl halide. Number two, reduction of alkyl halide. Reduction of alkyl halide. Alkyl halide reduced using active metal with hydrochloric acid or dilute acid with active metal like zinc. Active metal like zinc with dilute acid. What will happen is this X will be replaced by hydrogen. They can produce nascent hydrogen in the solution and you will get RH plus HX. So this RH, X will be replaced by hydrogen. For example, if you take CH3Cl, you will get CH4. Except fluoride, alkyl halides, chloride, bromide, iodide can be converted to corresponding alkane. Number two. So catalytic hydrogenation, number one. Reduction of alkyl halide, number two. A very popular reaction, many of you remember, Wood's reaction. Number three. Preparation of hydrocarbon alkane by alkyl halides, Wood's reaction. What is Wood's reaction? An alkyl halide treated with metallic sodium. An alkyl halide treated with metallic sodium. The reaction can be explained by two molecules drawn like this. The reaction happens in presence of dry ethereal solution. And you see the cleavage occur like this. It is cleaved like this. 2NaCl out. 2NaCl, that is 2NaX out. And you can see these R will be coupled with the R. The product obtained is RR. You get RR. Symmetrical higher alkanes. Symmetrical higher alkanes is the product. Symmetrical higher alkane is the product. The product obtained contain even number of carbon atom. If you take RX, the product is RR. For example, if you take CH3Br treated with metallic sodium, we can write two molecules to understand the reaction. And the reaction happens in presence of dry ether. It's going to cleave like this, NaBr out. Two molecules of NaBr out. And this CH3 will coupled with that CH3. And the product obtained will be CH3. You get ethane. You started with the methyl bromide. We got ethane. Methyl bromide, you get ethane. Ethyl bromide, you get symmetrical higher butane. So meth, you get ethane. Eth, you get butane. Prop, you get hexane, like that. Whatever you take on the reactant side, the product will be a exact multiple. If you take Rx, you get RR. If you take RX, you get RR. That is the importance of Wood's reaction. It is promoting symmetrical higher alkanes. Okay, so what if we are taking a mixture of RX, R-X? Suppose we are taking a mixture of two different alkyl halides. Suppose we are taking mixture of RX and R-X mixture for Wood's reaction. What will be the product? I am not asking. NCERT is asking. NCERT is asking you. Suppose you take a mixture of RX and R-X. What will be the product? You will get three possible products. Product number one, RR, self-coupling of RX. Product number two, R-R, That is product number 2, self-coupling of R dash X. And product number 3 of less probability, R dash. So you get 3 products. Self-coupling product of Rx, R, self-coupling products of R dash X, R dash, and intercoupling Rx, R dash X, you get R dash. 3 products are obtained. Remember, Woods reaction promote symmetrical higher alkanes. Is it clear? So reaction number 1, catalytic hydrogenation of alkene alkyne. Reaction number 2, reduction of alkyl halide. Reaction number 3, Woods reaction. Reaction number 4, decarboxylation reaction. Decarboxylation reaction. Decarboxylation reaction. If you take a carboxylic acid treated with soda lime. What is soda lime? NaOH calcium oxide combination is called soda lime. First you will get RCOONA and that interact with the NaOH in a dry condition maintained by calcium oxide, and the reaction can be illustrated like this. It is Na2CO3 out, Na2CO3 out, and this R gets this H. You get the product RH, that is alkane. This is decarboxylation reaction. This is descending reaction. Here one carbon is decreasing. If you take ethanoic acid, CH3COOH, you will get sodium ethanoate, and that interacting with NaOH, the reaction can be understood so happening and is Na2CO3 out, CH3 with H, the product is CH4. We started with ethanoic acid. We started with ethanoic acid and the product is methane. Methane. So ethanoic acid, you get methane. Propanoic acid, you get ethane. Butanoic acid, you get propane. Pentanoic acid, you get butane. Whichever acid you take, that COO out, you get the resultant product. If you take RCOOH, you just erase this. COO, you remove it. You remove COO, you remove this. The result will be RH. That is decarboxylation. Right? And a final method of preparation for alkane, Kolb electrolysis process. Kolb electrolytic process. Kolb's electrolysis. Kolb's electrolysis. Right? Here what we take is, we take a potassium or sodium salt of carboxylic acid and we do electrolyze. Sodium or potassium salt of carboxylic acid is taken and it is electrolyzed. Electrolysis is done. See, what is the product obtained and how do you get the reaction? Let me illustrate with the 2 molecules, RCOOK with another molecule, RCOOK. I will demonstrate how do you get the different products with the water in aqueous medium. With the water in aqueous medium, listen carefully how the product is obtained. It is going to cleave here. It is going to cleave here. This R and this R will couple. That is the product number 1 you get at anode. This is the alkane you get at anode. Right? Now, this is already ionized and these 2 will be removed as carbon dioxide. That too is obtained at anode. 2 carbon dioxide liberated at anode. So this you get at anode. Okay. Now, this is going to break here and K plus OH minus, K plus OH minus, 2 moles of KOH you get in the solution. 2 moles of KOH you found in the solution. And this H with this H removed as hydrogen. That is removed as hydrogen gas at cathode. So at the cathode, hydrogen gas is eliminated or removed. At anode, along with the carbon dioxide, we get our requisite product in the format RR. And in the solution, there is KOH. Let me explain with one example. Suppose I am taking one example, say sodium salt of acetic acid. If I am taking sodium salt of acetic acid, CH3COONA, very simple. CH3COONA. In the place of R, we have CH3. So what is the product at anode? CH3. So product at anode is RR. Here it is CH3. So this CH3 with this CH3 you get RR. This is product number 1, ethane. We get at anode. Carbon dioxide, 2 mole carbon dioxide at anode. And NaOH, 2 NaOH in the solution. 2 NaOH in the solution. And now hydrogen. You see, interaction with water. So NaOH, 2 NaOH, hydrogen. It is hydrogen at cathode. This is at cathode. This is at anode. So at the anode, you get a alkane along with evolving carbon dioxide. At the cathode, you get hydrogen. The detailed mechanism you must know. And there are several modifications of Kolbe reaction and its reactions. Examples where we get saturated monocarboxylic acid, you get alkane. Saturated dicarboxylic acid 1,2 position, you get alkene. Unsaturated dicarboxylic acid at a vicinal position, you get alkyne. All examples, if required, we can go through when we discuss the questions. These are the preparations involved in alkanes. Which are the preparations? Catalytic hydrogenation of alkene alkyne, reduction of alkyl halide, Wurtz reaction, decarboxylation reaction, and Kolbe's electrolytic reaction. Right? Is it clear? Next is properties of alkane. You can go through the physical properties which are commented in the text. We are concentrating on chemical properties. As already I have commented, alkanes are inert towards acids, bases, oxidizing agents, reducing agents, etc. But we have few reactions. One of the most important reaction is substitution reaction. See, hydrogen atom of alkane may be substituted by halogen, nitro group, sulfonic acid, etc. We are going to discuss in detail halogenation reaction. Substitution reaction of alkanes. Number 1, halogenation. That is free radical halogenation. If we take CH4, for example, when treated with chlorine in presence of light, there will be free radical substitution reaction. You will get CH3Cl plus HCl. And the importance of the reaction is it can give you multiple products. You may also get CH2Cl2 upon continuous reaction. You may also get CHCl3 with the elimination of HCl. You can get CCl4 with the elimination of HCl. You can get monohalogen derivative, monochloro, dichloro, trichloro, perchloro derivative. The entire hydrogen atom replaced by chlorine, perhalogen derivative. So it is a chain reaction, continuous reaction, involving a detailed mechanism we need to learn: chain initiation, chain propagation, chain termination. Three major steps involved in the mechanism: chain initiation, chain propagation, chain termination. What are all the, this is one example. So you get multiple products like this. It is a chain reaction. The reaction is initiated by homolytic fission of chlorine. So Cl2 chlorine undergo homolytic fission. In presence of light, you get two chlorine free radical, and that chlorine free radical attack methane, and you get methyl free radical releasing HCl. Now that methyl free radical interact with the chlorine, you get the first product CS3Cl plus Cl dot, and that CS3Cl may attack with the Cl dot. You get CH2Cl dot plus HCl, and that CH2Cl dot plus Cl2, you get a CH2Cl2 plus Cl dot. This is propagation. This is chain initiation. This is chain initiation. And what we are talking now is chain propagation. Chain propagation. So it is a continuous chain reaction. One attacks next, next attacks next. It goes on like that, giving multiple possible products. Here you get first product, here you are getting second product, and this reaction will continue. You will get CHCl3, you will get CCl4, like that. It's continuing reaction. And chain termination. Whenever two radicals meet, suppose you have a radical X meet with another radical X, it will be converted to X2. Suppose you have a radical N meeting with another radical N, you will get N2. Suppose you have X, a radical meeting with N, you will get XN. It will be terminating. So two radicals when we meet, that reaction will be terminated. Suppose in this case, suppose a chlorine free radical from the reaction mixture I am talking, from the reaction mixture, two chlorine free radical meet, it will be converted to Cl2. Suppose two methyl free radical if meet, it will be terminated. You get ethane. There is a question, why the reaction with the methane for free radical chlorination, some amount of ethane is obtained. So two methyl free radical ultimately can give you ethane. Okay, suppose a methyl free radical is meet with the chlorine free radical, you will get CH3Cl. So whenever two radicals meet, that chain will be terminated. So this is chain termination. Chain termination. So chain initiation, chain propagation, chain termination. Is it clear? That is free radical halogenation reaction. It's a free radical substitution reaction. Halogens attacks with the alkane. The vigorous reaction given by fluorine even in the darkness. Chlorine give the reaction in presence of light, while bromine, iodine less reactive, iodine least reactive. It's a reversible reaction, and we need to have some supporting oxidizing agents to promote the reaction. That is the trend of reaction given by free radical halogenation reaction for alkanes. Very important reaction. Another reaction given by alkanes, or we need to understand from alkanes, is combustion reaction. Combustion reaction. Combustion of alkanes. Very simple. Combustion reaction of alkanes. For example, suppose you encounter a question, how many moles of oxygen needed for the complete combustion of 1 mole butane or 1 mole propane? 1 mole propane to undergo complete combustion, how many moles of oxygen minimum required? Suppose you encounter a question. Very simple. Propane, C3H8, propane. It is burned with the oxygen, and you get 3 carbon atom, you will get 3 carbon dioxide. 8 hydrogen atom, you get 4 water molecules. So 1 mole propane can give you 3 mole carbon dioxide and 4 mole water. Over how much is oxygen? 3 into 2, 6 oxygen, 4 oxygen, 10 oxygen. So it will be 5 mole oxygen. So 1 mole propane requires 5 mole oxygen, the minimum. Minimum 5 mole oxygen is needed. So writing such a balanced equation regarding the combustion of alkane, that is the only point. Meanwhile, there are some controlled oxidation reaction given by alkanes. That is important. Controlled oxidation reaction given by alkanes. I was referring to combustion reaction, and this is the general equation for combustion reaction, which also better if you know the combustion reaction general equation. N number of carbon atom, N number of carbon dioxide, 2N plus 2 hydrogen atom, it will be N plus 1 water molecule, and oxygen will be 3N plus 1 by 2. General format. I was referring to the controlled oxidation reaction. Controlled oxidation reaction. There are 4 reactions. Controlled oxidation. Methane. Oxidized using copper catalyst 523 Kelvin 100 ATM. You are getting methanol. They are industrially, commercially important reactions. Make a special note on 2. While the same methane with the molybdenum oxide, you get methanol. While ethane with acetic manganese acetate, you get ethanoic acid. Generally, alkanes resist oxidation, but the alkane containing a tertiary hydrogen may be oxidized by KMnO4 to get an alcohol with a good yield. So 2-3 important controlled oxidation reactions are given. Methane with the copper catalyst giving methanol. Methane with the molybdenum oxide catalyst giving methanol. Ethane with the manganese acetate giving ethanoic acid. And oxidation of alkane with a tertiary hydrogen. Example, 2-methyl propane contain a tertiary hydrogen that can be oxidized to alcohol. These are some controlled oxidation reaction referred in the text. Make a special note on to that reaction. Another reactions given by alkanes explained in the text is isomerization reaction. Isomerization reaction. A given long chain alkane heated with the anhydrous aluminum chloride, you can see you get a branched chain molecules. Normal hexane converted to 2-methyl pentane, 3-methyl pentane. You are converting a normal chain into branched molecules. You are converting a normal chain into branched molecules. This is special in case of petroleum industry to improve the quality of petrol and improve the quality of petroleum products. These reactions are important. Isomerization. A given long chain, straight chain molecule converted to constitutional chain isomers. Isomerization reaction. Okay. There is another one very famous, aromatization. Aromatization. N-alkanes containing 6 or more carbon atom on heating to high temperature with a suitable catalyst. Earlier we were using platinum as catalyst. Nowadays the reactions are supported by chromium oxide, vanadium pentoxide, molybdenum oxide, high temperature pressure condition. Here we have 6 carbon atom normal hexane is converted to aromatic system. 6 carbon aromatic system, it is converted to benzene. First you will get cyclohexane and that will be dehydrogenated to get benzene. 6 carbon atom, you get benzene. 7 carbon atom, you will get toluene, like that. Like that. Okay, so 6 or more number of carbon atom upon heating with a suitable catalyst at a high temperature. Earlier we were using platinum. The reaction called reforming. The reaction called reforming, aromatization. It is basically involving dehydrogenation, removal of hydrogen. So first, the normal 6 chain carbon converted to cyclohexane. From there, it is converted to benzene or derivatives. 7 carbon atom, you may get toluene. 8 carbon atom, you may get ethyl benzene, xylenes, etc. Okay, like that. Earlier, the reaction may be called as, or it was famous known as platforming process. Platinum reforming process. Platforming process. Next one, reaction with the steam. With the steam, in presence of nickel catalyst, you get a water gas. Alkanes with the steam, you get a water gas, studied in the chapter hydrogen, syn gas, synthesis gas, water gas. There is a process, pyrolysis, cracking. Pyrolysis, cracking. Higher alkane heated to higher temperature. Higher alkane heated to higher temperature, called pyrolysis or cracking. We get simpler molecules. The molecule is broken to simpler molecules. Even sometimes we can make use of some catalyst also. You see dodecane, 12 carbon atom alkane converted to 7 carbon, 5 carbon and other product. You get simpler alkanes, alkenes, etc. Cracking. So whether isomerization, aromatization, cracking, pyrolysis, these are very popular in petroleum industries, used for improving the quality of petrol. And to wind up the segment alkane, we have one more topic, that is conformations. Hope you know conformations fall under stereochemistry. They are rotational isomers, conformational isomers. Conformations. They are obtained by free rotation through a sigma bond. Suppose we take ethane. It is explained somewhere in this area you can find. If you take the molecule ethane, CH3, the molecule may be represented like this. You see, CH3. Hope you find the two hydrogen atom coming in the same line. This way of representation, we call it as Sohor's projection. Or the same molecule you can represent with the Newman projection. This is Newman projection. This and this are same. This is carbon atom 1 which is represented here, and this is carbon atom 2 which is represented behind this disk drawn, and 3 hydrogen atom respectively, and they are coming in the same line. That is called eclipsed conformation. Now, this is an unstable situation, rather least stable situation, and you can find due to this hydrogen-hydrogen repulsion, this carbon-carbon sigma bond can undergo a free rotation. Suppose the backside carbon, I am demonstrating a free rotation through a dihedral angle 60 degree. Imagine the carbon, this carbon, along with the hydrogen, go for a free rotation through the sigma bond. This carbon, along with the hydrogen, undergo a free rotation through the sigma bond. The new configuration will be somewhat like this. The front carbon along with the hydrogen stay back, while the behind carbon go for a 60 degree rotation. It will form such a conformation. This is called a staggered conformation. This is eclipsed conformation. This is staggered conformation. Which is more stable? All of you know, staggered conformation is more stable as it is far away. So there is minimum repulsion. Minimum repulsion causes that to be pretty more stable. But remember, they cannot be isolated. The energy difference between eclipsed and staggered conformation is very low, that we are unable to isolate them. All of you know. Suppose we are moving on to another example. If we move on to another example, say butane, we can have conformations in butane. CH3, CH2, CH2, CH3. You can select any carbon. I am selecting these two carbon atom for drawing the conformations. You see conformation number 1. I am taking this carbon, 2 hydrogen and 1 CH3, 2 hydrogen and 1 CH3. Now this carbon behind the disk drawn, it is CH3 1 here and hydrogen 1, hydrogen 1. I am talking this carbon 2 hydrogen 1 methyl. This is fully eclipsed conformation. Fully eclipsed conformation. Even we call it as methyl eclipsed. Two methyl coming in the same position. That is methyl eclipse. Now imagine the behind carbon. That means this carbon along with the hydrogen and CH3, it make a 60-degree dihedral rotation. It undergo 60-degree rotation. You get a new conformation where the front carbon CH3 and 2 hydrogen stay back like that, and the behind carbon CH3 comes here and the 2 hydrogen comes here. We call it as Q conformation or Gauche conformation. Gauche conformation. Here we had only 2 conformation. Here we get extreme 4 conformations. Even though we say 2 conformation, 4 conformation, there are infinite number of conformations present. We are talking about extreme possibilities. Suppose the behind carbon make one more 60-degree rotation. Imagine the behind carbon along with the groups make another 60-degree rotation. You get a new conformation where CH3 like this, hydrogen, and the behind carbon CH3 comes here, hydrogen is here and hydrogen is here. That is called a partially eclipsed. Partially eclipsed. Or we call it as methyl hydrogen eclipse. Methyl hydrogen eclipse. And the last conformation, again 60-degree rotation, you get the last conformation. CH3, H, CH3, H. This is called anti-conformation. Anti-conformation. So, completely eclipsed, Gauche conformation, partially eclipsed, anti-conformation. And what is the order of stability? What is the order of stability? It is anti. Most stable is anti. What is next? Then it is Gauche. Then it is Gauche. Then it is partially eclipsed. And least one is fully eclipsed. That is the order of stability of various conformations. Okay? Even though it is not in the text, you need to know. Similarly, conformations of cyclohexane. Conformations of cyclohexane. Better to have an idea regarding conformations of cyclohexane. Cyclohexane we draw like this. Cyclohexane we draw like this. Actually, it is a puckered ring type structure having different possible extreme conformation. One conformation seems to be like this. It is called a chair conformation. Chair conformation. One conformation seems to be like this. We call it as boat conformation. One conformation seems to be like this. We call it as twist boat conformation. Twist boat conformation. And the one conformation seems to be like this. We call it as half chair conformation. Half chair conformation. And what is the order of stability? This is 1, this is 2, this is 3, this is 4. Which is expected to be most stable? Which is expected to be most stable? And the order of stability will be 1 is most stable. And after 1, it is 3, next stable. Then it is 2 and least stable is half chair conformation. That is the order of stability of conformations of cyclohexane. And I wish you try yourself to draw the various conformations of ethylene glycol, CH2OH, CH2OH. This is ethylene glycol. Taking these 2 carbon atoms, you can try drawing 4 conformations. You will get four conformation: completely eclipsed, gauche, partially eclipsed, and anti-conformation. Where I wish everybody try to explain. Here, anti is most stable. Here, anti is most stable. While if you try this one, of course, anti is stable, but the gauche conformation found to be pretty more stable than anti in this example. Try to illustrate how and why. I'm leaving to you. I'm leaving to you. If you try ethylene glycol, ethane 1,2-diol, you can draw four conformations. Not in the NCERT, but I'm insisting you to take up this challenge because this is previous year questions. These kind of questions we can expect from the concerned area. You try to draw the four conformations like what we did in this case. What we did in this case, you try to draw the four conformations of ethylene glycol. What are the four conformations? Fully eclipsed, gauche conformation, partially eclipsed, anti-conformation. What is order of stability? Anti, gauche, partially, fully. That is order of stability. So anti is usually most stable normally. Why most stable? The two bulky groups are coming opposite. But in this case, you can see the stability of gauche exceed anti. Try to find out why and what is the reason. That I am leaving to you. Right?